Yeah, thank you for showing up in this room. I'm really excited to talk about this topic. I didn't really know a lot about it when I submitted this. I had a manager at one time who encouraged me to submit conference talks on systems that we hadn't built yet, so that you had to build them in time for the conference. We call this conference-driven development. In this case, it's conference-driven learning. And what I'm going to talk about today is using napkin calculations or back-of-the-envelope calculations. We use them interchangeably to estimate the actual expected performance of a system in milliseconds, microseconds, even nanoseconds in some cases. And the reason why I think this is an important topic is because some of the engineers that I've observed around me, both at Spotify and at in the industry, is that they have a really good, sorry.
You have clip.
Oh, what?
You have a clip.
Oh yeah. I don't, great start. Okay, I guess it is early. Yeah. Okay, where was I? Yeah, so the engineers that I've observed in industry and around my peers tend to have a really good intuitive understanding of how fast a system should be for a certain action. So they have a really good understanding of, well, does the I/O speed here really matter for the overall performance of the system? How long might this take on the network? And I find that often something that may take a more inexperienced developer weeks to figure out, they can reason out in a few seconds because they've seen it before. So what I want to show to you in this talk is to give you a little bit of a shortcut, which for many engineers takes decades to build this experience, and a bit of a framework and methodology to do these kind of napkin calculations very rapidly. I wanted to start with a little bit of a gauge of the room. So earlier, a couple weeks ago, I was doing a test on this laptop where I had a local client written in Rust, so the performance is fine, and then a Redis instance. And I was doing some get operations with just 8 bytes. And I want to get a little bit of a feel of the room here for how long people in this room think that would take. So I'm going to start at 10 milliseconds and then go down in like sort of 10x down. So 10 milliseconds, 1 millisecond, 100 microseconds, 10 microseconds, and less than 1 microsecond. And I want you to raise your hand if you think that the actual performance of Redis on this machine for a get of 8 bytes is closest to that number. So let's start. Who thinks that it's closest to 10 milliseconds in performance? Please raise your hand. Okay, a few, not too many. 1 millisecond. Few more. 100 microseconds. Quite a few people. Okay, good. 10 microseconds. A little fewer. We have consensus around 100 microseconds. Who thinks that it takes less than 1 microsecond to do that operation on this laptop? No one. Okay. So we have consensus at around 100 microseconds if we look at this as a distribution. The actual time is around 25 microseconds, so 10 microseconds was the right one, the closest one. And by the end of this talk, you should have a bunch of numbers like that in your head to be able to get to that for a bunch of different problems that we'll look at today. So let's start by going to I think a really good example of someone who's really mastered thinking about systems from first principles and building up and building an expectation of cost and performance of them. So when Musk was in the middle of the 2000s, he was kind of trolling around the LA area, talking to aerospace engineers at Lockheed and NASA and so on, to try to figure out whether he could build an aerospace company. And one of the first problems you face as an aerospace company is that you need a rocket so you can propel whatever device you need into space. And when he went to, so he sort of asked NASA, and they said, well, it's probably around 130 million. The Russians could do it a little bit cheaper. But we were talking about $110 to $130 million for him to buy a rocket that would propel his spaceships or whatever he wanted to send into space. And this just wasn't really sufficient for what he needed, right? 130 million to send something into space didn't really allow him to build the crazy like Mars funneling company that he wanted to build. And so there's this really, I think, illuminating quote where essentially he looks at the rocket, but he doesn't look at the rocket as this thing that cost 120 million, but rather as this metal thing, right? So there's aluminum, maybe some cobalt for some strengthening the alloys. You have carbon fiber. You have all of these materials. And so he looks at the rocket and then thinks, okay, maybe it's 90% this, 10% this, lower numbers that add up to 100%. And then went on to, I think, his favorite website, the London Metal Exchange, and looked up the spot prices for all the different metals. And then he multiplied the weight of all the different materials with the spot price at the metal exchange in London and got some number. And that number was about 2 million. So orders of magnitude less than the actual cost of the rocket. Then he looks at the two numbers, 2 million and 120 million, and then of course he says, well, all of those 118 million is just inefficiencies, bureaucracies, and inefficiencies in manufacturing. And he was confident that he could do something much, much better by using modern manufacturing techniques, right? A lot of these rockets were invented during the Cold War, 3D printing and so on. And finally he got the Falcon 1 down to about a 7 million cost. But I think this is a really good example of using first principle thinking to go from something really complicated, distilling it down to the first principles, and then doing some simple math, and then seeing the discrepancy between his naive interpretation of what a rocket is and actual cost of a rocket, and then arriving somewhere much, much closer to the naive interpretation. Because when you have a gap between your expectation and the actual performance of a system or cost of a system, that gap is always going to be an opportunity either for you to correct your mental model of the system, or there's a huge opportunity. In this case, there's a big opportunity. So if we apply this to a more everyday example, a boring cloud bill that comes in once a month or whatever, we might have a cloud bill that's $100,000. Maybe it's $10,000 or whatever. And by boiling this down to first principles, you should very quickly be able to do a calculation along the lines of, let's say that this is a SaaS company, right? So you might say, well, I have 10,000 RPS. I know that I'm responding with about 100 milliseconds. I multiply those two numbers, and I know I have single-threaded workers, so that means that I require about 1,000 CPUs. I know that each CPU costs $10, so that means that I should be spending about $10,000 on my main application that's making me money, right? So that's the 10%. Maybe you're at 20% because, again, this is sort of napkin. You want a little bit of overhead to not run at 100% utilization. But where's that other 90% going? These are the kinds of calculations that you should be able to do very, very quickly in the middle of a meeting to arrive at some more interesting discussions and also not just eat up this cost, right? Maybe you're storing a bunch of data that you don't need to store, maybe you left some instances on, or maybe you're hugely over-provisioned. But again, the gap between your naive expectation and reality always presents an opportunity. So I'll present the first base rates here, and a base rate really is some kind of semi-constant number that's really useful to memorize so you can do these kinds of calculations. So in this case, I used the cost of a CPU. These are almost all very, very close to what it costs in a normal cloud, so not dedicated hardware, but in a cloud. This is what you can rent computers for on Amazon, Google, Microsoft. If your number is more than 100% greater than this, then you're paying too much for your compute, but it should be within 10 to 20% of here. I've just rounded the numbers a bit to make them easy to remember. It's kind of easy to remember because it's $10 per CPU, and then you kind of go down by an order of magnitude as the performance of your storage system decreases. These numbers are hugely useful, and I found myself using them in so many situations where we might, that's going to be too expensive to do. You do the math really quickly in your head, walking or in a meeting or on a whiteboard, and you say, no, it's not expensive at all, let's do it. And instead of having 4 meetings where in one meeting you're deciding that you need to figure this out, another meeting you're deciding who needs to figure it out, then in the third meeting you're deciding that this person is going to figure it out because the other person is now now somewhere else and working on another project, and in the fourth project they then come back with a very precise measurement that's way more precise than you actually needed. Instead, you can do this in 30 seconds if you remember these numbers. The other numbers that are useful to remember, and I'm going to present a bunch more in this talk, are the base rates for your application. So things like median response time, we used that before, how many transactions you do into a database, how many customers you have, throughput, and so on. These are all going to be very specific to your application. And if you see sort of the old timers at your company, you may see that they have a really good representation of how the app behaves in their head. So I'm going to go back to one other good example outside of computer engineering of someone who I think did an awesome job doing some really good napkin calculations. So this guy whose name I can barely pronounce, so I'm going to go with Eratosthenes, lived in 200 BC. And I don't know how of a controversial belief this was at the time, but he was pretty sure the Earth was round, and he wanted to figure out what the circumference of the globe was. Try to imagine how you would do this in 200 BC. What do you have available, right? Today, it would probably be pretty easy to do this. You can probably do something with a ruler and Google Earth in a heartbeat if you wanted to, or something much, much easier, and it's just would be very easy to look up. But Eratosthenes needed to come up with a more ingenious methodology of solving this impossible problem at an impossible time. So what he observed was that in Aswan, Egypt, at noon, the sun was directly overhead. And you could see that because he couldn't see his own shadow. It was directly on top of him. In Alexandria, there was a 7.2 degree angle of his shadow. And he knew the distance between Alexandria and Aswan. And now he knew this angle, and he knows that the whole globe is going to be 360 degrees. He divides that by 3.7. He gets that then the total circumference of Earth is going to be 50 times the distance between those two cities, and then arrives at a result that is within 3% of the number that we use today in 200 BC. At a time where the New World and Old World hadn't even met each other yet, right? Only in the 1700s, a bunch of Frenchmen who were figuring out the definition of a meter, only then was the number made more precise. And they had massive grants, 7 years, and a big team of people. And I always think of this guy, whose name I can't pronounce, every time someone tells me that we can't measure something. So here's kind of the idea of using very, very simple calculations to figure this out. The last guy I'll present you to until we go into just computer-related examples is Fermi. So Fermi was a physicist who worked on the Manhattan Project, and he was really revered among his colleagues for his remarkable ability to estimate things very, very quickly and surprisingly accurately. When they were detonating the first nuclear bomb in New Mexico, he dropped a couple of scraps of paper, and based on the distance that they traveled from where he dropped them from, he was able to estimate that the yield of the atomic bomb, of which there had never been detonated one in the US before, was 10 kilotons. The real answer, which they only got to through laborious calculation over several, I'm assuming days or hours, you didn't really have much compute power available in the 40s, they were at around 18 kilotons, right? The first time anyone had ever let loose one of these bombs in the Western world, right, he was able to estimate that very, very accurately. So what Fermi is really famous for are these Fermi problems. And you may have heard this one before of how many piano tuners are there in Chicago. Now this is obviously a super ridiculous question and not even that interesting. But the methodology that he uses to figure out an answer to this through some very simple numbers that probably all of you have in your heads is really interesting. And you could imagine how you could use this to solve almost impossible problems very quickly in computers, but also something along the lines of if we put solar cells on all roofs in Chicago, would we be able to self-sustain the city in terms of energy? You would be able to estimate that through the same methodology. So what he does is he just kind of notes down a bunch of things that he knows. So there's about 9 million in Chicago's metro area. If you live in America, I'm sure you probably remember something like that. There's maybe around 2 people per household. 1 in 20 households has a piano. So this is the kind of thing that you might not quite remember, but you might sort of agree that, okay, 1 in 50 is maybe a little bit too rarely, 1 in 5 is too much, so this seems like roughly correct. Pianos are tuned once a year. I don't know if that's true. I don't think my grandparents have tuned their piano in 15 years. But you could imagine maybe something roughly like that. We can tune that and get a bit of a bookend. Tuning, it takes maybe 2 hours. Piano tuners work on a very American schedule here. 2 weeks of vacation a year, 8 hours a day. And you then combine all of these numbers and you get how many piano tunings are going to happen per year, how many piano tunings can each piano tuner do. You combine those numbers and you get that there's probably around 225 piano tuners in Chicago, right? And we arrived here from some very, very simple numbers, and we can see how this could apply to thousands of other questions that we might ask ourselves. Now, of course, the answer is not 225 piano tuners. It would be presumptuous of us to assume that we've arrived at the right answer. But it's probably within an order of magnitude of the right answer. Like, I'd be willing to bet money that it's somewhere between 20 and 2,000, with kind of the peak probability at probably around 225 and scattered around the low hundreds, right? So What Fermi and Musk observed is that most of the time you need a lot less precision than you think. I read in a book that I was reading in preparation for this talk that if we polled this entire room for their age, we only needed to poll, if we only polled 5 people in this entire room for their age, we would have a 95% chance that the median would be within that tiny population. Today, we talk a lot about how we need so much data, 10 to the 20th or whatever data points in order to say anything with accuracy. But a lot of the time, we need a lot less data than we think for the kinds of decisions we need to make, right? Musk doesn't need to know that it can cost him exactly, 2,200,021 blah, 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 blah cents to build the rocket. He just directionally needs to know that it can be a lot cheaper than that 120 million when you just look at the raw materials. A lot of the decisions we make, we just need a general direction. And what I find that a lot of decision makers in software design do is that they prefer to have very exact calculations, but then they only have time to evaluate maybe 1 or 2 options. What I find is much superior, and a lot of the decision research I've read agrees with this, is to go much wider with much less accuracy in your calculations. You're able to evaluate a lot more solutions a lot more quickly. So let's try to use Fermi decomposition of a problem on a real problem. Now we get into the more computer part of this talk. So a problem that I had, and all the problems here are problems that I've actually had, which may make them a little boring, but they're at least real, was that a couple of years ago, we started very seriously investing in our failover architecture from one region to another. And as part of that, you need to do a bunch of things. You need to fail over your read replica of your database to become the writer in the other region, wait for it to catch up. And we also had all these in-memory data stores. And these in-memory data stores had some data that was important but not critical to lose, things like sessions. And we would like to try to restore that in the new region and get all the data transferred over. But the data store we were using, we were not really very comfortable with the replication, and we'd had some bad experiences with that in the past. So what I wish would have happened was that, or something that could have happened at the time, was that we could have said, well, what if we do the most naive thing possible? Dump the entire memory to disk, transfer it over the network, and then restore it in the other region. Well, was it feasible to do that within the constraints of the couple of seconds that we want to fail over in? So again, we can use some of these base rates again of how a computer performs. So we read from disk, we write to disk, we read from memory, write to disk, then we transfer it over the network, then we read again from disk, and we write all of those all of that memory into the target region, right? So what you can see from here as well is that there's really only one number that matters here, which is the network from one region to the other. All the other numbers don't really matter too much. And this is only for one. I'm just going to use gigabyte and gebibyte interchangeably because gebibyte is terrible to pronounce. So 1 gigabyte transferring that takes about a minute, and we have 16 of them. So that would take about 15 minutes. Even assuming a very generous compression ratio of 2 or 3 times, we're talking minutes to fail this over, which is just not feasible. Now, this result alone is really, really feasible. As the example of below, or that I had earlier of like having all these meetings, instead you can just say in the meeting, oh, could we do this? Blah, 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 like walk through these rates. Okay, IO is this, sketch it out in 30 seconds, and say, no, this is not feasible. If we want to do this, we need to invest in some kind of incremental transfer of data through replication or inspecting the LRU for the most hot keys and only transfer those, or something different. Unfortunately, we can't do the most naive thing here. So with that, I'll take a little bit of a discourse, because at this point, it may remind you of big O notation, which is used in algorithms and data structure resource to tell us something about how many times we need to look at a piece of data. So if you have an O of n algorithm, then it means that you need to look at every single element once. If you have an n squared algorithm, it means that every time you look at one element, you also need to look at every other element. The problem with big O notation is that it's not very sympathetic to how the hardware underneath performs. So if we take a very exaggerated example, if we have an O of n algorithm that's doing random SSD seeks, so seeking randomly on disk for every single element, then random memory access, I don't know why this is not going up to 4,000, but is 4,000 times faster to do random memory access than random SSD access. So big O notation is good for algorithms research, but at this day and age, it's very, very rare that we find an improvement in the big O of an implementation. Most of the algorithms and data structure research today is about having more what's called mechanical sympathy. So more sympathy for how the hardware works, using CPU caches, using the NUMA architecture properly, limiting I/O, using as much sequential I/O as possible, and all these things that are more relevant to how the computers actually behave. The other thing that's the problem with big O notation is that it doesn't tell us any expected number. If our program is running in 10 milliseconds, we have no idea, given big O, whether that's fast or slow. That's why we need something a little bit more sophisticated. So just earlier, I mentioned a bunch of numbers that I was using in this failover scenario. And this is, by the way, this whole thing is not my idea at all. It was popularized by Jeff Dean, and a lot of these numbers are floating around, and I guarantee a lot of you have seen them before. I spent some time writing a Rust program to try to replicate those numbers and see what they would be on my laptop, and so that I can run them in our production systems and see what they would evolve into. And here, a lot of the time, you only get the latency number, so how long does it take to do an SSD read of 8 kilobytes in 1 microsecond. But I also really wanted to know what it would take to read a megabyte, a gigabyte, and things like that, because that's something that we find ourselves doing. And just staring at these numbers alone can be really, really helpful, because we see something like how sequential SSD reads are remarkably fast. In terms of throughput. We're getting pretty close to the same throughput from reading from disk sequentially as we're getting from memory, but the latency is a lot higher. So these observations are interesting. Another thing you could take out of this is how a TCP echo server, so what you may have written at some point where you have a server that's just responding to whatever the client is sending. If you're doing that with just 8 bytes or so, or 8 bytes, or 64 bytes, sorry, then you're getting an overhead about 15 microseconds. Remember the Redis example in the beginning where it was around 25 or so microseconds? Well, most of that overhead you can now see is from actually just the TCP and traversing the kernel stack. We're only spending about 10 microseconds or so in Redis actually getting things from memory, parsing the protocol, and so on. Similarly, if you have a proxy that's spending 1 millisecond in overhead, well, that's a really terrible proxy, because you can see that from a very simple proxy should be spending just in the tens of microseconds, not in the hundreds of thousands of microseconds. So something else that I thought of while making this talk is that maybe some of you want to practice this kind of thing, because to recognize these problems, you need to have this kind of as a sharp tool. So I created this little mailing list, and if enough of you sign up for it, then I might start emailing a problem that needs to use these base rates and send resources along about once a month. But this link will be in the slide later as well, but just syrupson.com/napkin. So let's now take an existing system, right? One of the things that was really interesting about the example with Musk was how he created an expectation of the system and then took the difference between the actual system and his expectation, and then the difference between them found an opportunity. So a problem that I encountered a while ago was that we were having Australian merchants reporting a 2 to 3 second response time for their sites. And this didn't really jive with my intuition. Like, we render a page in about 100 milliseconds. The round trip time between Australia and DC, which is where our data centers are close to, is 250 milliseconds. There should be about 4.5 to 5 round trip. You add all of those numbers up and you get about a second. So why is this taking 2 to 3 seconds, right? Why is there this 1 to 2 second gap between what my Napkin Math is telling me and the actual system's performance? So again, is this because there's a bug, an opportunity in the system, or is there a bug in my mental model of the system? So it turns out, in this case, it's a bug in my understanding. And what I remembered is that TCP has slow start, right? It doesn't know the size of the pipe between the client and the server, so it can't send all the data at long. It needs to kind of try to inch its way to figure out what the bandwidth is between the client and the server. So what TCP does is that initially it will send 15 kilobytes from the server to the client. That's the default in Linux. You can tune it, but 15 kilobytes is very standard. Then in the next one, if all of those packets made it safely to the client, it's going to send 30, then 60, then 120, and so on and so forth. And then what I graphed was, well, how much data is transferred after how many round trips? So my assumption of 1 round trip for HTTP was wrong. It depends on the size. And when I look at these merchant sites, some of them were 150 kilobytes, right? So it requires 3 full round trips on that initial connection. So this was a gap in my understanding, and now what I found in my personal website, I thought I was making everything fast by base 64 encoding images, but that actually just got the size above 15 kilobytes. So if your site is below 15 kilobytes, it's the fastest possible, right? And if it's above that, you're gonna have a little bit more trouble. So this was also, I think, an interesting example of doing the napkin calculation, looking at the difference, and then getting a new appreciation of the understanding. And of course, you want to memorize some of these base rates as well of how fast packets transfer around the globe. I find that if you remember these, you can generally figure out from one point to another within 50 milliseconds or so how fast the packet will go from A to B. So finally, I want to talk about this very real problem that we have at Shopify. So fundamentally, Shopify is about showing, or a big part of Shopify, now we do a lot more, but the original Shopify experience was that you had an online store. And what is an online store fundamentally about? Well, it's about narrowing down what it is that you want to purchase, right? A merchant has potentially millions, hundreds of thousands of products, and you need to find the one that's just for you. And so you're gonna go to the men's collection, it's gonna show you everything from men's, or you're gonna go to the women's collection, and in there you might filter, oh, I want to see only dresses, or I wanna see only shoes, and you end up with all of these rules applied, like I only wanna see shoes, they need to have shoelaces, they need to be brown, I want them to have cat in the title for whatever reason, and you just kind of keep layering on all of this until you find the thing you want. So the first part of solving any complicated, sufficiently complicated problem is to start to really define the problem. So first we say, we kind of place the assumption and do the Fermi decomposition of this, saying, okay, there's probably around 2 million or so products for a merchant. Then we say that a collection can filter it by up to 64 rules, right? You're adding rules, the merchant is adding some rules, and there's about 64 of those. And each one of those rules can take the form of, it contains the string cat, or the price is less than $300, and so on and so forth. Each product then has all of these fields attached to it, like what is the average rating, and what is A, and what is B. And on average, these product rows are maybe gonna take up about half a kilobyte of just information about that product. Then what we want to do is that we want to serve queries that are nailing down the products that we want. So in this case, I'm just writing this out as SQL, just because it's something that most people are familiar with. But we want all the product IDs where the price is less than $200, the product description has sneaker in it, the product rating is more than 3, and the product color is either black, yellow, or red. We want to order that by the product color, and we want to get page 10. And if you've spent a lot of time with SQL, you will understand how the database will cry if it sees a query like this for a sufficiently large merchant. So this is a problematic query, and we have this constraint that we want to serve this really fast so that your browsing experience and your filtering experience is fast. So the first thing you do is, the way that I like to think about it is as sort of a decision tree. So at the root of it, you have the problem that you're trying to solve, and you're continuing to try to refine and make it as concrete as possible. So it looks more and more like a physics problem that you might have been handed in high school, and less like this abstract thing with people in the room arguing about which kind of features they want. So the first thing to do then is that you consider the naive solution. So you do kind of the napkin math. Okay, we have these like 2 to the 21st products. Each of them is half a kilobyte. You kind of multiply some of these numbers together, and you arrive at, okay, this is probably about a gigabyte of data for that worst case merchant. So how long does it take to traverse 100 or 1 gigabyte of memory sequentially? About 100 milliseconds, we remember that from earlier. So is that feasible? Well, not really, right? We wanted less than 10 millisecond response times. But it does tell us something useful, right? Like 100 milliseconds to traverse all of that data is still, it's pretty good. It could be a lot better, but it's pretty good, and maybe we can use some of that naivety in our solution. So 100 milliseconds for like the most naive solution we possibly can is pretty good. So we might kind of try to consider another dimension. Maybe an inverted index as a data structure could be useful. MySQL is not going to be very good at these like wildcard matches of sneaker. It just doesn't really cope very well with the data structures that it uses. So what is an inverted index? Well, you can think of as an inverted index where you have a big hash map, and the key in the hash map is a string. In this case, it will be all of the words in your product descriptions and product titles. So for example, we might have a sneaker that's called like Big Yeezy sneaker or whatever they're called, and then sneaker would be a key in that inverted index. The value for sneaker would then be all of the product IDs that have sneaker in the title. And then we can do these kind of wildcard queries very, very fast, because we can then just look at all the products in there and then filter further. So we might, well, maybe an inverted index is really useful to serve some of this. We don't really know. Doing the like less than and equals than, less than, greater than operations are going to be a bit tricky with something like this, but maybe it's useful for part of the operations. And when we do the math, we sort of like, we say, okay, each title is maybe a maximum of 13 words. The descriptions maybe on average like 27 words. So the total size of this whole index is only going to be 64 megs. We also know from earlier that a gigabyte of RAM costs about $1, and so 64 megabytes is in the low cents. This seems economical as well. So this is kind of an interesting result as well. So then something else we might look at is, well, right now these collections are stored in MySQL. That's kind of slow. Well, is it slow because B trees are fundamentally a poor data structure for these kinds of things? And we could imagine doing a little bit more napkin calculations of seeing, well, for 64 of these rules, how much do we narrow it down? And going back to the problem and looking at what would the shape of the problem have to be for the B trees to be really good. Now, this is very unsatisfying because I don't know the solution to this problem. If you have some ideas, let me know. But this is really to illustrate the process of using napkin calculations to go wide. I said earlier that I think it's vastly superior to go wide with approximator calculations than just go like all in on trying to use B trees and do all the exact calculations. And you're also just going to fall in love with that solution very easily. And I really think that breaking down the problem that way and continuing to go back to refine it is really required if you want to step out of the box of iterative improvements. If you need to make an order of magnitude improvement to your design, you really need to understand the abstraction levels below you. You need to understand the layers around you and put the puzzle together in a completely new way. You just can't do step changes or order of magnitude improvements of your systems if you're only iterating and confining yourself to the abstraction that you're currently at. You're gonna have to combine more things around you. So finally, how do you memorize and practice these base rates, first principle thinking, and the Fermi decomposition of problems? For some reason, today, memorization is this like thing that we shouldn't practice, and it's I don't really know why it's gotten this reputation, because I find it immensely useful. The excuse is that you can just whip out this on your phone, but a lot of the time we don't. Like that friction of going into your phone and finding the base rate and things like that, you're not as likely to do that when you find yourself needing this in the middle of a conversation over dinner with only napkins available or in a whiteboard. You need to memorize these numbers. They're not that hard to memorize. What I recommend is you can use space repetition, which is essentially it shows you these base rates on an exponential schedule so that you will remember them. There's software called Anki, which is kind of a power tool to do that. If you're not familiar with flashcards, there's a messenger bot called Communis, where essentially you can tell it like, hey, I want to remember this, and then it will send you messages once in a while asking you, hey, do you remember how long it takes to read a gigabyte from an SSD? And then if you answer incorrectly, it will show it to you more often. That's a really good way of doing it. The other way is to sign up for those periodic challenges that I mentioned earlier, so you get something in your inbox once in a while to practice this. You can also spend some time developing your own base rates. If you're interested in mechanical sympathy and understanding more about how computers work, it's a really good way of doing it. You can read the source of my project. There's a lot of base rates that are missing, that are in the README, that you can contribute if you'd like to, but that's a really good way of remembering these numbers as well. And then finally, of course, applying these numbers to your own systems, right? I'm sure that you right now have a problem that is begging for some napkin calculations, or you have a problem where you can widen the search space of solutions that you're going for dramatically that way. As I said earlier, I think that napkin calculations are great because every time you do a napkin calculation and you look at the real system's performance and you look at that difference, there's always an opportunity either for you to improve the system or improve your mental model of the system. Thank you.
Thank you, Simon. We have 5 minutes for questions. So, anyone?
So I'm going to pose a problem to you that I was listening to a podcast, and one of the things on the podcast, AT&T was pushing 5G Wi-Fi, 5G cellular service. It's going to be great. It's going to be so much faster. That and he talked about the speed at which you can get data on your phone, and the thing that he said was using 5G, you'll be able to have a surgeon in LA do surgery on a patient in New York. And I thought to myself, and this is what I kind of want to puzzle this through, like, is that possible? So you're going to have a robotic toolkit that's in a patient that's being controlled by someone in LA. So it's dominated by the round trip time, the 60 millisecond round trip time. And I thought, I don't care how fast I can get cell speed from here to the cell tower. It matters that New York to LA thing. And I thought the last thing I want is for that to happen to me. So let me puzzle that through. Is that something that would be possible to make happen if you've got toolkits? It seems to me you're going to need a lot more AI to control the speed of the tools, and I don't know. Just because I don't think you're going to be able to get the accuracy and the quickness. The tool starts moving towards something, and it starts to bump into something, and you want to stop it anyhow. So
yeah. It's so funny you mentioned this because just as a quick aside before going into that, I was going to have a part of my presentation about sort of decision making in software, and one of the problems there, or one of the examples I had, is that we always assume that if the problem is really big, we need a really big and complicated solution. And what you're seeing in the medical field, that one of the examples I was going to give, right, is that if surgeons use a checklist to just go through everything before the surgery, there's a 10% or whatever decrease in mortality rates, right? And so one of the things I posited was okay, let's say you instead invested the 10 million robotic arm. Is that going to decrease your fatality rate more than doing something simple like a checklist? And I kind of wonder if that also applies here, right? I find it a weird example from AT&T because, yeah, I would also say it's latency dominated, right? And I don't really, you should be able to get high fidelity video over just fiber. So yeah, I'm also puzzled by it. I don't really understand why that was an example of 5G.
I just think that it was a great way to toss something out that nobody would understand, and it sounds absolutely terrific. And so go buy 5G now.
Yeah. No, I'm glad it went through your filter, and you're like, no, this is bullshit, because it sounds like it's this. Yeah. I mean, it's probably great, but I don't think it's a 5G. It's not 5G enabled, right? Probably 5G is going to be more about sending videos and social media than things like that.
Well, the other thing about 5G was that I doubt the surgeon's going to be sitting somewhere doing it on his cell phone using 5G. He's probably going to be in an office that's hardwired with fiber rather than on his cell phone. Please, I don't want him on.
I'm just imagining the scenario of a surgeon sitting in a Starbucks, oh, this is great, 5G is best. This seems like something where you should be in a room with 10 feet of metal to make sure you're not interrupted. I don't know.
I agree, yeah.
In here, the human reactions is half a second, the feedback between your hand and your brain. So from my point of view, 60 milliseconds is not the most important factor in that computation.
There we go.
That's an awesome example of using base rates, right? You're well, this is the same example as the failover, right? Well, actually, this latency doesn't matter at all. It's all about the human reaction time, right? And I'm sure there's also something to be said about whether you're going to be able to, do people have the same actions through a screen as they would have in person? I don't know. That would also be interesting.
Terrific. So 500 milliseconds versus the 60 millisecond round trip time.
Thank you. Any more questions?
Here.
Otherwise, I'll be up here and at the booth.
Oh, one question as well.
Thank you. Could you go back to that earlier slide that said order of magnitudes, et cetera, et cetera?
This one?
Yeah, that's one of the most impressive slides that I've seen in the last number of years. And it's certainly something that I've been fighting over throughout most of my career. Where did you arrive at that? Is that something that you gradually arrived? Did you find it somewhere? Is this your own personal wisdom? And if not, I was curious how you got there or where you found that.
Yeah. There's this secret book. No. This quote is not over from anywhere specifically, and if it probably is from somewhere that I don't remember, right? It's like kind of like you read a book that you haven't read in a long time and you recognize a lot of ideas that you didn't attribute to there. But no, I wrote this. I think I've been really fascinated in the past year about sort of like scientific advancement and reading about like the invention of the steam engine and things like that, and like how we got from like even whaling, like how do we get out of whaling to have light and things like that. And I feel like one of the things that all of these inventors have in common, and I'm using Elon Musk as a modern example because most people in the room would be familiar with him, is that they just tend to have such a deep understanding of the systems. And I keep seeing that in my colleagues around me as well. There's a guy sitting in the room here, and like what I learned from him is he just continues to just be in the source code of whatever system that is underneath the one that might be having a problem. And he's always opening the source code. And people in meetings who are doing the same thing, right? And the people who don't tend to do that, they tend to be too constrained. They tend to think about the problem and the attributes of the problem rather than the fundamental data structures and the shape of the numbers and data. So I can't attribute this to one source, but I think if you look at history through this lens, I think it's something that a lot of those great inventors have in common.
So, thank you so much. A round of applause for our speaker, please.